Okay, let's see how you made out with graphing this exponential function. To start with, I put down a function that we're familiar with that's related to what we want to get to here. We looked a little earlier at y equals 3 to the power x, and it's that classic exponential shape, right? The more you go to the right, the steeper and steeper it gets. It's increasing, it's increasing. Okay, now, we noticed that if you put a negative sign in front of the exponent here, this thing's going to spin around the y-axis, right? Because we noticed that y equals 3 to the negative x is just the same as 1/3 to the positive x, right? So the curve would be reversed. We would get the mirror image of it like this. So that takes care of this feature of this equation. But we're also subtracting 2. But we know that for any function such as this parabola, if you subtract 2, it moves down 2 places. So the green dotted curve here, that has to shift down 2 places. So instead of going through positive 1 on the y-axis, it's going to go through negative 1. And this curve here, its horizontal asymptote was the x-axis. Now, the horizontal asymptote will be x equals -2, right? This horizontal line here at -2. The rest of the curve will be just shaped like this, but of course going up. So our curve looks like that. If we get rid of this other stuff, there's a pretty decent drawing of what it should look like. Okay. That's pretty good. Let's look at some real life problems. Modeling with exponential functions. This is on page 318 of your textbook. There are basically 2 situations that exponential functions apply to. One is a case of growth, like we saw the paramecia in that first example growing. They would double every hour. So that meant that the more paramecia you had, the faster it kept growing, and things kept speeding up, speeding up. The other phenomenon is decay, the reverse of growth. Something starts to decay and decays at a certain speed, but then as there's less and less of it left, that rate has to slow down. So it's just the reverse of growth. Look at example 4. Let's read that on the bottom of page 318. Inflation. That's another phenomenon that behaves this way. Suppose that inflation is predicted to average 4% per year for each year from 2012 to 2025. This means that an item that costs $10,000 one year will cost $10,000 times 1.04 the next year. You might say, why is that? Well, if something costs $10,000 and in a year from now it's going to be increased by 4%, that means the new cost will be that $10,000 plus 4% of 10,000, right? And another way of writing that is just 10,000 plus 0.04 of that 10,000, right? Multiplying the 10,000 by 0.04. Well, this is just 1 times 10,000 plus 0.04 times 10,000. So, I mean, if you wanted to use the distributive rule and be very formal about this, you would say, oh, I can factor out the 10,000s, and it turns out to be well, I guess I shouldn't say equal here. I should say it's going to. I'll draw a big thick arrow instead. If that's the case, then I should be multiplying my 10,000 by 1.04 to increase it by 4%. And that's where this number here comes from. If something increases by 4%, that means you're multiplying it by 1.04. So in part A and parts B and part C, it's asking us some questions. But this is covered in a video in your MML. So I'm going to give you an MML video homework, and there's also a good animation in there too that I'll assign to you. And that will cover this example. In class here, let's go to example 6 on page 320. And it's an example of decay, and this is not covered in an MML video. Example 6 says sales decay. It pays to advertise, and it is frequently true that weekly sales will drop rapidly for many products after an advertising campaign ends. This decline in sales is called sales decay. Suppose that the decay in the sales of a product is given by this equation here, where X is the number of weeks after the end of a sales campaign. Use this function to answer the following. A, what is the level of sales when the advertising campaign ends? Well, let's figure that out. As soon as the advertising campaign ends, how many weeks is that? Well, that's X equals 0, right? Because X equals the number of weeks after the campaign ends. So in part A, we're basically asked to figure out what is S when X is 0. We see that S equals 1,000 times 2 to the negative 0.5 times 0. So I'm replacing X with 0. That looks like a 6. Let's make that a 0. So that $1,000 in sales, what's going to happen to it? Well, negative 0.5 times 0 is just 0. Any number, any non-zero number raised to the 0th power is 1. So this is just 1 times 1,000, which makes sense because we're selling $1,000 a week at the moment the sales campaign ends. All right, so that's what that says. In part B, I say, all right, what happens after 1 week? Sales are going to go down. I have to take my formula and replace X with 1. So this is 2 to the negative 0.5 power. And you can tap on your calculator, or you could convert this to a radical. Keep in mind, this is 1,000 times 2, 2 to the negative 1. That just means 1/2, right? So that takes care of the minus sign. Any number to the power of 0.5 just means take the square root of it. So I'll do that in the next step. Okay. And this square root of 1/2, that can be computed on your calculator, or you might happen to know what the square root of 2 is, and that'll help you out. You're going to get $707.11. And then finally, we're asked to graph this. I'll make a graph like this and indicate 12 weeks. 4, 6, 8, 10, 12. 2, 4, 6, 8, 10, 12. And then here, sales. 4, 8, 1200. So that's my x-axis. This is actually my s-axis. We've used s as the variable name. So we say $400 in sales, $800 in sales, $1,200 in sales. At the end of the advertising campaign, we're saying x is 0 there. And sales were 1,000. So our curve's going to begin there. After, in part C, we're asked, use a graph to estimate the week in which sales equal 500. Well, we know that after 1 week, sales were 707, right? So it would be that point there. And this is an exponential function, right? So it's going to have that curve right there, asymptotic to the x-axis. Notice that the curve doesn't go out here because that's not in our domain. We can't talk about negative time. So, after how many weeks will we be around 500? 500 is going to be right about there. So it hits the curve right there. So how many weeks does that look like? Looks like about 2 to me, right? 2 weeks would correspond to about $500 in sales. And then finally they ask, does the graph show that sales ever fall to 100? No, the graph shows that, we know that the function's an exponential function, and we see that the asymptote is the x-axis. So the graph gets forever closer and closer to the x-axis, to where s is 0, but it never gets there. So now we can talk about our mathematical model that we're using in this type of problem. The exponential decay model, this is on page 320 near the bottom. Exponential decay is this type of equation. There's a base, it's a constant, being raised to some exponent. The variable is x, k is just some other constant that might be multiplying x. And then the whole thing can be multiplied by yet another constant, a. The requirements we make are that b is greater than 1, your base is greater than 1. A is a positive number, k is a negative number. So in the problem we just saw, our formula, and I have a version of it right here, our formula looked like that. Right, there was our x with a negative constant multiplying it. The base was greater than 1. And in fact the number playing the role of a is also greater than 1. So it matches up with that. But keep in mind, as I just showed you a minute ago, raising 2 to a negative exponent is the same as raising 1/2 to the positive version of that exponent. Now in this case, it doesn't look like that. B is less than 1, so it doesn't match up with that. The other model is this. So we can put the word or here. Let's write down the model. Well, of course, this looks the same. We're just going to change what these constants are allowed to be. In this case, b is a positive number, but it's between 0 and 1. A is still positive, but now we're going to insist that k be positive instead of negative. So we have a change here and a change here. And that's what we see. B is between 0 and 1. K is a positive number multiplying the variable. And it's just another way of looking at the same equation. Okay, let's work out number 37 on page 323, rather 324. Number 37, it's sales decay again. In fact, it's the same exact problem we just did with the numbers changed. But go work through that one and make sure you can handle it on your own.